Hello and welcome. This is the second day in 8 days problem solving series where we are solving selected but challenging problems of JEE Advanced 2020 paper 1. Today we are going to discuss a nice problem which tests your understanding about continuity and differentiability of real valued functions. We are given a function fx is equal to x cube minus x square plus x minus 1 into sin x and g be an arbitrary function. We are asked to hunt the right options among the given 4 options, which mainly comments on the continuity or differentiability of one of the functions, fx into gx or gx, in relative to the given status of other. Each option is an implication statement. It is a common mistake to confuse an implication statement with its converse. We should carefully see what is in if part and what is in then part. Let's examine each option one by one. Option A states if g is continuous at x is equal to 1, then fg is differentiable at x is equal to 1. We quickly notice that f is a continuous and a differentiable function for all real numbers because it is the sum of differentiable functions. Option A is essentially asking whether the product of two functions is differentiable, out of which one is differentiable and other is continuous. It is not hard to prove that the product of two differentiable functions is differentiable. But the situation becomes interesting when we replace one differentiable function by mere a continuous one. Can we get the same output even if we weaken the input? In other words, if we multiply a differentiable and a continuous functions, do we get a differentiable function? Of course, the product is continuous, but we are interested in figuring out whether the product is differentiable or not. In general, the answer is no. We can quickly get a counter example by noticing that the product of 1 and mod x is not differentiable at x is equal to 0, where 1 is a differentiable and mod x is continuous at x is equal to 0. So can we conclude that option A is wrong? We should not impatiently conclude that option A is wrong. It might be possible that the result which is not true in general but is true in some special cases. In other words, it might be possible that fx has some nice property which makes fx into gx a differentiable function. So it is worth to work with fx particularly before concluding option A wrong. So we simply find the derivative of fx into gx at x is equal to 1 by first principle. And eventually we get its value a finite number. It means fx into gx is differentiable at x is equal to 1. Therefore, option A is surprisingly true. It means our guess was correct that the product of a differentiable and a non-differentiable continuous function might be differentiable in some special cases, as we see now that fx into gx is differentiable at x is equal to 1. But the prime question is, why is this happening at all? Is fx carrying some nice property which is helpful in making fx into gx differentiable? The answer is yes. The so-called nice property which fx is carrying is f1 is equal to 0. It is the f1 is equal to 0 which nullifies the effect of non-differentiability of gx and makes the product fx into gx differentiable at x is equal to 1. Let's see what happens if f1 were not 0. If f1 were not 0, then there existed a neighborhood of 1 in which f was non-zero. It means we could find its reciprocal 1 over f in the neighborhood, and we were able to write g as a product of two differentiable functions, 1 over f and f into g. The differentiability of f into g and of 1 over f would make g differentiable, which is a contradiction because g is not necessarily a differentiable function. In other words, the product of a non-zero differentiable function and a non-differentiable continuous function cannot be differentiable because it implies a contradiction, as we saw just before. If you are a beginner in calculus, then it might be hard for you to swallow this argument right now. This argument is using some standard results of calculus, but we are not going into it in this video because it would be a long digression. If you want, you can ask in the comment section. As a conclusion, we mark option A right. Let's move to option B. In this option, we are given that fg is differentiable at x is equal to 1. and we are asked to figure out whether g is continuous at x is equal to 1. Notice that the option B is the converse of option A. We have already proved that a continuous g can make f into g differentiable. Now the question is, can some discontinuous g2 make f into g differentiable? Because if it were so, then the differentiability of f into g would not depend on the continuity of g. In other words, the differentiability of f into g would not imply the continuity of g, and that would make option B false. Equivalently, if somehow we get success to weaken the if part of option A with keeping the then part intact, I repeat, if somehow we get success to weaken the if part of option A with keeping the then part intact, then it would show option B wrong. Or we can put it in this way. If we get success in finding some function g which is discontinuous at x is equal to 1, but f into g is differentiable, then it would show option B wrong. Now the question is, can we find such a discontinuous function g? But the deeper question is, who is motivating us to find such a function? The motivation comes from the observation that we have already noticed that the derivative of fx into gx at x is equal to 1 is equal to f dash 1 into limit h tending to 0 g1 plus h. It means that the value of f g dash 1 depends on the limiting value of gx when x approaches 1. I repeat, the value of f g dash 1 depends on the limiting value of gx when x approaches 1, which is not necessarily equal to g1. This motivates us to hunt for a discontinuous function g for which f into g is differentiable. Once we understand what we are looking for, and more importantly, why we are looking for, then it is not very difficult to hunt it. Let's consider a function gx which is defined piecewise. Gx is 1 for x is equal to 1, otherwise it is equal to 2. It is clear that g is discontinuous at x is equal to 1. But notice that fx into gx is differentiable at x is equal to 1. This shows option B false. Once we are done with the first two options, the rest two options are easy to deal with. We noticed that the statement in option A is the stronger statement than in option C. It means trueness of A implies the trueness of C. Also notice that the statement in option B is weaker than in option D. So the falsity of B implies the falsity of D. Finally, we conclude that the correct options are A and C. This completes the solution. This was an excellent problem which tests our ability of differentiability for the product of two functions. This problem is able to shake you up if you are someone who has a shallow understanding of calculus. Calculus is a subject which is intuitively easy to understand, but the beauty of calculus lies in its rigor, not in intuition. If you are someone who doesn't cuddle with the epsilon and delta, the chances are high someone sold you calculus in the box of algebra. That's it in this video. We shall take an amazing problem on complex numbers in the next video. Make sure you attempt it before watching the solution. See you next time.